Our next speaker, Dr. Glenn Morrison, is a professor of environmental science and engineering at the University, I should say the University of North Carolina. His research is primarily focused on indoor atmospheric physics and chemistry. He has a particular expertise in the interfacial surface chemistry and will share how the contents of a building can continuously participate in chemistry that increase human exposures to pollutants or can be harnessed to the benefit of the occupants. Can't wait to hear.
Okay. Hi. So what I'm going to talk about is actually very related to what Cora was talking about at the very end there, and it's a good segue. And actually I'm going to talk about this in somewhat broader terms. In fact, thermodynamic terms, but don't worry. So when we are exposed to pollutants, we accumulate pollutants from our environment if we are in contact with an environment, either directly or indirectly, that has that pollutant, and the chemical activity of that pollutant is higher in that environment than in us. This is a driving force. Okay, this isn't true in every single case, but it's mostly true. So you can think of this a bit like temperature. So when you have a hot object and a cold object and they're in the same environment, heat will flow from the hot object to the cold object as long as they're somehow in contact with one another. And that's what this chemical activity idea really is like. Now, I really like to think of it in terms of reservoirs. So if we think of, let's say this couch here is a reservoir of flame retardants, as Heather showed, and she's nodding her head saying, that's not big enough, right? It's got to be a bigger reservoir. But the air is a much smaller reservoir for that same pollutant. There's some in it, but it's a smaller box in a sense. And we are somewhere in between. We could take on some pollutants. Now, these are reservoirs, but there's this idea that you can see it right here, that there's a flow from one side to another. And so it's chemical activity, actually, in our case, that's driving this exposure. And if we think of the height of these reservoirs as the chemical activity, this concept of chemical activity, where the chemical activity is quite high in this first reservoir, in this couch, and it's somewhat lower in us because we're taking it in and perhaps metabolizing these chemicals, then in general what you have is a net chemical uptake towards us. Now, how might you deal with this? Well, obviously the first thing you would do is try to get rid of the couch if you knew that this was a problem. But as you've seen in several talks, some of these pollutants that are in our environments are legacy chemicals. They're there, they've got there 30 years ago and they're still there. And we can't necessarily clean up every house. We can build a new building that is as clean as we can make it, but there's going to be buildings out there for many decades that are contaminated. So how do we deal with this? Well, what we could do, if we can't get rid of the source directly, is we can drive down at least the activity in the environments that we're closest in contact with, like the air in this case. So one way to do that would be add some additional sinks, something that draws down this activity which would lower our uptake rate of these chemicals. And so that's actually what Cora was talking about. Basically, let's find a way to get rid of the HONO by putting a sink in there, something that drives the HONO down. So surfaces indoors, as we've heard several times, Rich talked about it early on, Cora talked about it, are really, really useful. And one of the reasons they're useful is that there's so much surface area available. So they've talked about 300 times outdoor. Well, I like to think of it this way. What you see around us, that sort of available surface area, that projected surface area, is about 2 to 3 square meters per cubic meter. When air pollutants can interact with it, they can only get to it so fast, and that's something we call mass transfer coefficient, which is somewhere around 1 to 5 meters per hour. When you combine those together, you get a number that's actually equivalent to a clean air exchange rate if you're removing all the molecules as fast as you can. So if these surfaces were cleaning the air by just absorbing chemicals, that's equivalent of having a very, very high clean air rate coming into a building. So let's do a thought experiment here. Let's say, actually I'll do the thought experiment in a moment. I want to talk about one more thing first. So you've heard the term semi-volatile organic compound a lot today. Alan Goldstein, I think, may have been the first to introduce it. I'm not sure. But anyway, it's basically a kind of a sticky compound, the lower volatility sticky compound. Back in around 2001, Mike Van Looy at Lawrence Berkeley Laboratory and colleagues were injecting nicotine into a large room-sized chamber to look at how it would absorb to carpet, adsorb to carpet. And what they observed is that when you inject nicotine, it goes up really high in the room, and it would stay high if there was nothing for it to absorb to. But because there was carpet there, the concentration dropped very rapidly because the carpet was such a big reservoir. In fact, that's what you would expect with any semi-volatile organic compound, because it turns out textiles have a huge capacity to absorb organic compounds. And there's a lot of data that's come out in the past 20 years on this, and we've studied it in many different ways. And so these textiles can actually do a good job as long as they are at a lower chemical activity than the environment they're in for that chemical of interest. So now we'll do a thought experiment. So let's say we use this idea of clean textiles. So once every 20 years or so, you replace your carpet, okay? When you put in new carpet, let's assume for the moment it is quite clean, that it does not have phthalates in it, it doesn't have flame retardants, it doesn't have these things we worry about in it. That means that it's at a very low chemical activity, and therefore it's a sink. But over time, it will start absorbing these chemicals and become less of a sink. What you'd see here is this is a simulation, because I'm a modeler in the Moki group, and I have to do simulations. Early on, the concentration in the house on average would be quite low because it's such a good sink and it has such a lot of surface area. Over time, the concentration would go up and it would become less effective, but your average exposure would be lower than if it wasn't there. Now, what if you said, well, let's do something else. Let's clean it every 5 years in some way, and you'd actually ultimately reduce your exposure quite a bit. Now, this speaks to only one chemical, because I only simulated this compound called dibutyl phthalate, but it would work for a large classes of compounds that are semi-volatile. But I'm also not considering the sustainability component of this. What happens when you clean this? How is it clean? That's another question. But in theory, surfaces have a great potential to reduce your exposure. Textiles can work in another way. So in Denmark a few years ago, my colleagues and I exposed people to phthalates. And we did this in I know it sounds terrible, but it wasn't so bad. So we did this because we wanted to understand the mechanisms by which we absorb chemicals from the environment through our skin. And so we essentially put 3 people at a time into this chamber, it's basically a room, with somewhat elevated concentration of dibutyl phthalate and another phthalate. One person's wearing clean clothing with a low chemical activity of these phthalates, and 2 people are basically naked. And they're wearing breathing hoods, and you can see them here. I made sure that I was the one wearing clothing. And then we have these our other colleagues who were fortunate enough to go naked. Not quite naked. And so, but what we learned from this is quite astonishing in the sense that these phthalates, they're in the air, they're at concentrations that are relatively high compared to what's in a home. But it turns out that clothing is very, very effective at protecting you from those phthalates as long as it is clean. So what you see here is, there's actually 2 words that are not showing up here, but this is the person with wearing clothing, and this is the excretion rate, or I should say the total excreted over time of a metabolite of that phthalate that has been absorbed through the skin. And so the bare skin individuals had a much, much higher uptake through their skin, and the clothed individual, me, had much less. If I don't show it on this figure because I was going to emphasize the effectiveness, but if you actually look at we actually did an experiment where I had hung clothes in the chamber to allow it to come to the same activity as the room, chemical activity. My exposure is way up here. So clothing is very, very important, but it can be very, very protective. So let me give you a few other examples. Let's talk not about textiles, but all other surfaces. So temperature is very, very important. Rich pointed it out. I think Alan pointed it out, somebody else pointed it out. There were several people who pointed out temperature as being really important. Well, it turns out that for semi-volatile organic compounds, the emission rates are very, very strongly dependent on temperature, but also the chemical activity at surfaces that can adsorb are very sensitive to temperature. And if you did the following in buildings, if you had day-night cycles when people were present or not present, and you just changed the temperature in a clever way, you could actually reduce exposure in that building just by slight changes in the temperature. Cooler when people are there, warmer when people aren't there. I talked to Bill Banfleth about this earlier. Something where we have to pull the building people together to say, is this a viable and economical way to reduce exposure? Similar to that, consider carbon dioxide. That's one of these things, it's a product of us. We can't not have that source in our, 1 minute, okay. I have 2, okay, sorry, I can't read. We emit CO2, we can't help it. How do we deal with that? Well, think about it this way. So let's say we have a naturally ventilated building that has people in it, and the CO2 concentration rises during the day, and then when they leave, it goes down at night. If you instead paint the walls with a CO2 absorbing material that lightly absorbs CO2, we put out a lot of CO2. We can't absorb enough CO2 to paint walls with this and have it absorb forever. But at night, if it desorbs because the chemical activity gradient has changed, then we would see a situation like this where you buffer CO2. And in fact, this is proposed in this paper in which they actually develop materials just for this purpose. To be quick, because I only have a few more minutes, ozone is one of those compounds that we can actually, instead of adsorb, we can destroy at the surfaces, either by chemical reactions with organics or by chemical reactions that basically decompose ozone. And Rich Corsi's group has done a lot of work with this where they've studied materials and their longevity, which was one of Mary's questions. Can these materials do something like this effectively for a long period of time? In fact, it looks like many materials probably can. We know that the reactions of surfaces with ozones can go on for quite a while. And not only that they can be cost effective. The cost to install materials like clay paint, this is Aaron Darling's work, is not that much, especially if you consider that you might just be using this for people who are especially sensitive to outdoor air pollution. All right, I have 30 seconds left. This is almost my last slide. One last example. When you change the chemical activity of some chemicals, you can drive them off surfaces, and in particular, this might be useful for remediation. Richard Corsi and I studied methamphetamine for a few years, actually funded by NIST, and we found that methamphetamine is very sensitive to the amount of humidity is available, and so the activity goes up when the humidity goes up, and this will drive methamphetamine off drywall. So these are just a few ideas. As my last slide, I swear, Mary, I'm almost done. There's actually many, many more examples I could give you of this kind of thing. There's things we should consider, though. You consider these activity gradients. You consider that the activity that you're trying to drive down, that this is it could be for one chemical or for classes of chemicals, but you need to look at this kind of holistically. So when you try to control CO2, you also want to consider controlling other bioeffluents that may also influence your indoor air quality. I'm going to say one last thing because the last one is that I really think what we really need to do in these cases is field interventions. We need to go out in the field and install these things and see if they really do drive down exposure as expected. And this means doing everything from measuring exposure to measuring the chemistry on the surfaces in the field. And with that, I am done. These are a bunch of people I worked with. Thanks.
Okay, so Dr. Morrison, you get a question too. No, you don't have to necessarily come back, as long as your mic is working. Let's make sure everybody.
Is that working? Okay.
Perfect. Okay, so my question is, when you're looking at certain products to become sinks for some of these pollutants that are in the indoor environment. Is there ever a concern that there might be a reaction that happens within, so let's say, the carpet or the gypsum or something, right? And residuals start to happen?
Oh, sure, that's always a consideration. For many of the chemicals that we're looking at, that I've considered, they're fairly stable. You know, these flame retardants are fairly stable, unless you're in certain conditions, the phthalates are fairly stable. But yes, that's always a question. It's, you know, so, yes, of course.
Okay, so maybe we should take that into consideration when we are looking at that as a solution for.
Sure. I'd say the one thing we know about, of course, is ozone. When you react, when ozone is being removed at surfaces, oftentimes it does generate a new pollutant that we have to be concerned about. And so you want to have materials that don't do that.
Okay.
And we know that things like concrete and clay, these kinds of materials are good at that.
Right.
Yeah.
Perfect.
Yeah, hi, Bill Bonfluff, Penn State. So Glenn, when I bought my new house 25 years ago, it was fully carpeted, and the first thing we did was rip out all the carpets because it had hardwood floors. And that's often seen as being a way of improving air quality because carpets are notorious particulate sinks. In fact, they used air blown through dirty carpets to determine the olfactory load from buildings. But you're saying it's a gas sink that might be useful. So how do we reconcile those two points of view?
Sure. I mean, I guess the carpet has to be clean to begin with, obviously, and that has to, in order for it to absorb anything. But you're right. I mean, over time, it's going to accumulate detritus debris that does have its own, you know, the microbial activity generating VOCs, and so it's not a panacea. So the question is how can this work in a real environment in the best way? And maybe it isn't carpet, maybe it's ceiling tiles. You know,
Sure, I know you're just giving examples. In a similar vein, where do I have to store my clothes so that when I put them on clean, they're not already contaminated?
Oh, yes, there's an easy answer, outside.
Outside, that was going to be my solution.
Okay, so we have a question through Twitter. This question is for Dr. Shiriewa. How long do the crusts last? Do the surface crusts regenerate, as Dr. Corsi mentioned this morning?
How long what?
The crust on
Crust.
The crusts last.
Surface crust.
Yes.
Oh. So for this, I think this person is talking about this film in indoor films.
Okay.
Surface crust formation.
Okay. They haven't mentioned that.
Yes.
Okay, but once it's generated, as long as you don't clean it, it should be there for a long time.
For a long time.
Yeah.
Okay. They haven't added any further clarification, so we're going to leave it at that unless they want to write in again.
Can I just jump in? I think that they were asking about regeneration, and that the crust doesn't prevent the completely the ozone from penetrating.
Yes.
It
Ozone can
just
still
slows it
penetrate.
down.
Yes, it slows down.
Yeah.
Yes.
Perfect. Thank you. Yes, sir.
Yeah, just a comment or question on Cora's presentation. You talked about the stoves and how the electric stove did not give off emissions. And, you know, of course, since most electricity is generated through fossil fuels, you're changing the place where the combustion happens. So did you take into account, you know, the shift in air pollution?
Sure, I guess it just depends on where, well, and not all, in Ontario, we call electricity hydro, like that's, you pay your hydro bill. Yeah, so not all electricity is generated by combustion, first of all. But yes, that is a concern. Having point sources versus many non-point sources is something to think about, but it really depends on where where you're most concerned about the emissions and where it's easiest to remediate them.
Perfect. Okay, do we have any other questions?
Yes.
Oh,
Yes.
perfect. Thanks, Annette.
So I have a question for Dr. Morrison. This is Annette Olson, AAAS, and actually maybe also for Dr. Corsi. You talked about the meth labs, not meth labs, but the houses that were contaminated
That
with
was, yeah, that was, it was in the right direction, yes.
Yeah, yeah. So how did that work start, get involved? Were there people who called y'all, I'm from Texas, sorry, called y'all up to say, we have this question, and what is the role in this potentially for forensics?
Sure. We actually were contacted originally by NIST, who were interested in this work and wanted to support some chemistry studies on methamphetamine. And we, I don't recall more than that, other than that it was that interest, and we defined the research questions that we thought were most important in this, in which was, what is the form of methamphetamine? How is it remediated? How does it transport through building materials? Dustin Popendick was very involved in that work. And so in terms of building forensics, certainly if you're considering, forensics generally applies to law enforcement. And that means that if you're looking for whether methamphetamine is available, then you could, some of the work we've done actually speaks to that. What we did learn in that realm was that you could often have very clean surfaces, which is their standard, right? Generally the standard, you look for the amount of surface contamination, and not find anything, but still have a contaminated building because the methamphetamine penetrates beyond the surface into the building materials, into the drywall behind. So in terms of your specific question, it's relevant because forensics don't always catch what's there and tell you, whether or not the building's remediated.
Okay, any other questions? All right, well that ends us right at 7 minutes. It's perfect. Thank you all for coming up and for being a part of this great talk. I really look forward to what else you do with your studies. Thank you.